This is a video for AQA Mechanics, Work, Energy and Power, section 2.1, where we're looking at Hooke's law. Well, up until now, we've made an assumption that strings are inextensible. This is very much a modelling assumption so that we can, in some situations, say that the length of a string is going to stay constant throughout the motion. However, that, as I say, is very much a modelling consideration, and any string is going to have some extension when a force is applied to it. So what we want to do now is to consider how the forces and the extension are related to each other in strings and springs. This takes into account something called their elasticity. First of all, what do we mean by strings and springs? Well, a string is something which only has a force in it if it's extended, so if we pull on it, or it goes into what's called tension. On the other hand, springs have forces if we compress them or extend them. So they have forces which are called tension when they're extended, or compression forces when they're reduced in length. Hooke found by experiment that the extension in a string or a spring is directly proportional to the force applied. So if we look at this diagram here, in the first part of the diagram we have a spring at its natural length L with no weight added onto it. But if we put a single weight on there, let's call that W, then it extends by some distance x. And if we put a second one equal to that, so we've got now 2W acting down, then the extension has gone up to 2x. So a diagram of force against extension is a straight line through the origin. So there we've got our force is proportional to the extension, or force is equal to a constant multiplied by x, the extension. It doesn't continue in that way. If we were to keep going on increasing the force, eventually the spring would give way and go past its point of elasticity, and so the extension would come like that, and then it wouldn't return to its natural length L. But within this region we have that the force is proportional to the extension, or force is equal to kx. Now the constant k is not normally expressed in that way. We normally talk about force is equal to lambda x over L, where lambda is something called the modulus of elasticity. L is the natural length of the spring and x is the extension. So the idea that k is equal to lambda over L. So there's our expression. As I say, lambda is called the modulus of elasticity, and it has units of newtons. And L is the natural length of the spring. So we could think of that as F is equal to Kx, and K is then referred to as the spring constant, or stiffness, and that will have units of newtons meter to the minus 1. I'm going to illustrate using these two formulae now with a few examples. So in the first example we have a string of natural length 1.5, so we've got L equal to 1.5. The modulus of elasticity, lambda, is equal to 50 newtons, and we have it stretched to a length of 2 meters. So therefore the extension x is equal to 2 minus 1.5, which is equal to 0.5 meters. So the tension T is equal to lambda x over L, and that's equal to 50 multiplied by 0.5, the extension, over 1.5. So that gives us 50 over 3, which to three significant figures is 16.7. This is a tension or a force, so 16.7 newtons. In the second problem, then, we have a mass of 0.5 kilograms hung from a string of length 15 centimeters, and then it hangs in equilibrium, so this is it hanging in equilibrium here at a point 18 centimeters below the suspension. So we've gone from a natural length of 15 centimeters to an extension equal to 3 centimeters. And then we've got two forces acting. The tension in the string due to it being extended, and the weight downwards, mg. So we can say that those are equal and opposite to each other, so therefore T is equal to mg, but T is lambda x over L, so we've got lambda, x is 3, we can use centimeters for both of these, so we've got 3 times lambda, and L is 15, and that must be equal to the mass 0.5 multiplied by 9.8. And if you rearrange that, we find that lambda is equal to 24.5, and that will be newtons. In this next example, we've got a block resting on a spring, and we've got a stiffness constant of 200 newtons per meter. So now again, this time a force upwards pushing, it's in compression this time, on the block from the spring, and the weight mg acting downwards. It's in equilibrium, so again we can say that T is equal to mg, but this time T is given by kx. So we've got kx is mg, or that the extension x is equal to mg over k, and that's equal to mass 4 multiplied by 9.8 divided by 200, which gives us a value of 0.196. That will be meters, or if you wanted to express it in centimeters, 19.6 centimeters. In the final example, we've got a mass of 5 kilograms attached to one end of a string of length 4 meters. We're then going to pull it down to 6 meters below its point of suspension. So we've got an extension in the string x equal to 2 meters with a natural length of 4 meters, and that produces a force upwards T given by Hooke's law. There's a force downwards equal to mg, which is 5g newtons. So those forces not in equilibrium this time, so that we have then got some acceleration, which, let's assume that the acceleration is upwards, and therefore we can say that T minus mg is equal to the mass times acceleration, ma. T we can find by Newton's laws, so T is equal to lambda 150, the extension 2, divided by the natural length, which is 4. And that gives us a value T is equal to 75 newtons. So substituting that into the equation above, we have that 75 minus 5 multiplied by 9.8 is equal to 5 times the acceleration. And that gives us a value of the acceleration equal to 5.2 meters per second squared. And there we are with the solution typed out nice and neatly for you. Well, that's the end of this video on Hooke's law, and in the next video we'll be considering the idea of elastic potential energy.